Hello Bobcats. So today in this video we will be discussing precipitation reactions. And precipitation reactions are also under the category of double replacement reactions. And this will kind of follow in the same order as the single replacement in that we will be writing a formula equation because there will be ionic compounds involved. In fact, precipitation reactions are about ionic compounds. And then we will do a total ionic and a net ionic. So let's write the a formula equation first. So let's say we have lead 2 nitrate, so we take lead 2 nitrate, PbNO3, 2, it's aqueous. We're going to add potassium, 2 moles of potassium potassium iodide. This will be aqueous, and then it will produce lead 2 iodide, which is a solid, and 2 moles of potassium nitrate, which is aqueous. Okay. So the reason we know that this is also a double replacement is if we look at this, we see that these are 2 ionic compounds in solution. Pb is a 2 plus charge, nitrate has a 1 minus charge, potassium has a 1 plus, iodide has a 1 minus. So the double replacement is that this positive charge, this cation, will go with this anion, and this cation will go with that. So we have a double replacement. So the positive with the negative, positive with the negative. And the reason they're called precipitation reactions is because in order for the reaction to occur, you have to form a solid from the mixture of the 2 solutions. So in this case we have a solid. Now as we go through this, we also have the total ionic. Remember in the last video we talked about how any ionic compound that is aqueous we dissociate and we think of those ions in solution. So let's look at a total ionic equation. Total ionic equation. Now the ions dissociate, but remember we are going to not write them as aqueous even though we understand that they will be aqueous. So we have the lead 2 plus ion plus there's 2 nitrates. That subscript means there's 2 nitrates, so we have 2 moles of NO3 1 minus ions in solution, and then we are going to have 2 times the potassium, so that's 2 moles of potassium 1 plus ions, and then 2 times iodide, that's 2 moles of I 1 minus ions. And these are coefficients saying that I have 2 of those ions. Now over on this side, the product, this forms a solid, and the solids are not dissociated, so we rewrite that as is because it is a solid. And then over here this is aqueous, so it dissociates, so we have 2 moles of K1 plus and 2 moles of NO3 1 minus. I ran out of space there. So when we look at both sides, we notice that the 2 moles of NO3 are exactly the same on both sides. So we have this one and this one are considered spectator ions. And then the potassium 1 plus is exactly the same, so it's a spectator. So our net ionic equation, the one which doesn't include all of the spectator ions, the net ionic equation in this case is going to be those ions that did not change. So we have the lead 2 plus, which is aqueous, plus 2 I1 minus ions, which are iodide ions, which are aqueous, will react to produce a precipitate or solid potassium iodide. And this is the reaction that's occurring in here. Now, a lot of times on exams or in other cases, they just ask for, most of the time you'll get asked for a formula equation and the net ionic. We don't usually ask for a total ionic. The total ionic is just showing you what we have. So if we had a beaker of lead 2 nitrate, we'd have a beaker with lead ions and 2 nitrate ions, a ratio of 1 to 2 ions in that beaker. And then in this beaker we'd have a ratio of 1 to 1 of potassium and iodide. And then when you mix the two beakers together and all the ions get to interact, it's the lead and the iodide ions that form the solid. The potassium nitrate stay in solution, so they really do not do any reacting. So this is our net ionic, and the easiest way to determine the net ionic without having to go through all of the total ionic reaction is to look at the precipitate that was formed. And all you would have to do really is to write the precipitate that's formed as a product, and then realize that on the reactant side it's the ions that make the precipitate. So your net ionic equation is just the 2 ions that make your precipitate. And then of course, to determine the spectator ions, an easy way to do it without writing out the whole total ionic equation. So my spectator ions are just taking the product that stays aqueous, so the product that stays aqueous, and dissociating it. And so when I dissociate the potassium nitrate, I have 2 moles of K plus that are aqueous, and that should be and, not plus, but this should be and 2 moles of the nitrate 1 minus ions that are aqueous. So these are my spectator ions. So again, the net ionic comes from the solid that is formed, and so you would just take the solid as the product, and on the reactant side write the ions that make the product, and then the spectator ions are just taking the aqueous product and dissociating them into their ions. Now, so again, what this would look like in a beaker is I would have, let's say I'd have a beaker here of water solution, and remember the lead 2 nitrate are aqueous, so there's a Pb2 plus ions floating around, and then we'd have 2 nitrate ions in solution. Okay? And then if we take that and add the other beaker, which now in this case shows 2 potassiums and 2 iodides, so it's a K1 plus, potassium 1 plus, let's say an iodide 1 minus, and an iodide 1 minus. And when we mix these two solutions, so when I pour this into this, what we get is a solid that forms, and you can think of it as that the solid is on the bottom, so I'm just going to draw it in a different color so you realize that we have a solid down here, and it would be the lead iodide solid, and then in solution remains the potassium ions and the nitrate ions, and they do not react. So that's what we're seeing when we do this reaction. Now, the next thing we need to talk about on double replacement or precipitation reactions is the solubility rules. In other words, how do I know when something is going to become a solid when it reacts or stays aqueous when it reacts? So we use what are called solubility rules. And this is something that you're going to have to memorize because you do not get a table for the test. So you need to work work at memorizing these solubility rules. Now, what are the solubility rules? These are rules used to determine what products in a precipitation reaction will become solid or will precipitate. In other words, become solid. So remember, the precipitate is the solid that forms when two solutions are mixed and react. Now, we need to define a couple of things before we get started on solubility rules. First, what does soluble mean? Soluble means that it dissolves in water. It could be other solvents, but we're talking about water right now. And usually something that is soluble we consider to be aqueous. So whenever you see the AQ symbol, that is something that is soluble. It's aqueous. And insoluble is defined as does not dissolve in water. Water. So something that is insoluble will form a precipitate, or we can say is the solid, and we use that symbol for it. Okay, so if it is soluble, we say it's aqueous. If it's insoluble, we say it is solid, and therefore is the precipitate that is formed because it does not dissolve in water. So now we need to look at a solubility rule table and go over it to make sure you understand how to read it. This is one that I have available, and you'll notice here that I've got it in set up where we see everything above here. So I'm going to draw a line here. All of these ions up here are soluble unless there's an exception, okay? And then all of these are insoluble unless these are the exceptions. So, and then you'll notice that it's also divided into, these are cations, and these are the only cations that we deal with for solubility rules. So this is the cations on the solubility rules. And then all the others, we're looking at the anions. Yep, I misspelled it. Cations. And then everything else is an anion. Okay, so as I look at this, I think that anything that has group 1, and remember group 1 cations are lithium, sodium, potassium, rubidium, cesium, and you can even think of hydrogen as one of them. okay, hydrogen. And these cations, anything that has these cations, group 1 cations, are always soluble. There are no exceptions, so they're always aqueous. Anything with ammonia as the cation is also always soluble, no exceptions. Now let's look at the anions. Anything with nitrate as an anion is always soluble, no exceptions. Chlorates and perchlorates are always soluble, no exceptions. Anything with an acetate, it could be iron acetate, it could be sodium acetate, it could be any acetate, it doesn't matter. Magnesium acetate, they're always soluble, no exceptions. And then this is a bicarbonate, they're always soluble, no exceptions. Now here we start to have some exceptions. Our chlorides are halides, so we have chloride, bromide, and iodide. Those are the halides. And the halides are always soluble unless it is silver, mercury, or lead. So if you have like silver chloride, it will be a solid. Or if you have lead 2 iodide, it will be a solid. The fluorides, all fluorides are soluble unless it is the silver, mercury, lead, and then you combine also like calcium fluoride, strontium fluoride, or barium fluoride. You'll notice there's a group here that tend to be parts of the exceptions, and if you look at the periodic table, that group is from group 2, and it's the calcium, strontium, and barium in group 2. So it's these 3 that tend to make the exceptions. So again, if we look at sulfates as the anion, all sulfates are soluble unless it's like silver sulfate or lead 2 sulfate or calcium sulfate. Calcium sulfate is insoluble, or strontium sulfate, insoluble, meaning it will be a solid. And then we have these anions, and these are all insoluble. So all hydroxides are insoluble unless it's a group 1 ammonia or calcium, strontium, barium. So in other words, something like calcium hydroxide would be soluble, or strontium hydroxide will be soluble. And remember, anything with group 1 and ammonia, doesn't matter what, are always soluble. So that's why these are exceptions for the insoluble ones, the ones that become solids. Carbonates, phosphates, chromates, and sulfides are all the same. They're all insoluble no matter what, unless it's group 1 or ammonia. So that's how I would read it. So if I want to look at some compounds and decide whether it's soluble or insoluble, let's do a few practice ones. So let's see, let's say I've got lithium sulfate. So I look at I realize that this has got group 1, lithium's group 1, so this is always soluble, so this would be aqueous. Or if I have, let's say I have silver nitrate. We notice, so I'm looking here, that's a group 1. I notice this anion, all nitrates are always soluble no matter what, so it's aqueous. Let's say I have lead 2 bromide. Well, I'm going to look at the anion, the bromide here, and I notice that the bromides are all soluble unless it's got lead, silver, or mercury. So this has got lead bromide, so this would be a solid. Or what if I have magnesium carbonate? So I look at the carbonate, I go up here, here's my carbonates. All carbonates are insoluble, meaning they're solids, unless it's group 1 or ammonia, and magnesium's a group 2, so this would be a solid. So you have to decide looking at either the cation or the anion. So if you have a cation, like let's say we have ammonium hydroxide, or let's make it ammonium phosphate. So I have ammonium phosphate. Now I could look at the phosphate and go, okay, phosphates, all phosphates are insoluble unless it's group 1 or ammonia. But the first thing I notice is that I look at, and there's ammonia, and we know that all ammonias are soluble or aqueous, and there's no exception. So it doesn't matter. As long if I see ammonia or a group 1 to start with, I know they're always aqueous. And then just one more. Let's say I have calcium hydroxide. Okay. So now I look at my hydroxides, and all hydroxides are solids or insoluble unless it's got group 1, ammonia, calcium, strontium, or barium. Well, there's calcium, so that means this is the exception, and it would be soluble or aqueous. So that's how we go about deciding from the solubility rules. Now we're going to practice one more problem, and then that will be the end of precipitation reaction video. So the next problem that we're going to look at, let's just practice this. So we'll look at, let's take, and sometimes you'll just get a word problem such as this. So let's write this as practice. Let's call this a practice. Okay, and let's say we have solutions of iron 3 nitrate and potassium hydroxide are mixed. So when I have these solutions of these ions, they get mixed and a reaction occurs. So the first thing we have to understand is that anytime I see words like that say problems that say solutions, and I know I have 2 ionic compounds, we know it's going to be a double replacement, and in this case specifically a precipitation reaction. So the first thing you have to do is you've got to write the correct formulas down and balance the equation. So we're going to write the formula equation, and in this case we know that this iron 3 means that that iron is a 3+, and that this, we know nitrate's a 1-. So that means I need 3 nitrates to go with 1 iron. So I'm going to write FeNO3, 3, and all nitrates, well, it says solution, so we know it's aqueous, but we also know it's aqueous because all nitrates are aqueous. We're going to add potassium hydroxide. Now potassium is in group 1, it's a 1+. Hydroxide is a polyatomic ion, it's a 1-, so it's a 1-to-1 ratio. So we're going to have potassium hydroxide aqueous, and we know it's aqueous because it's got group 1 with it. And as I do this, I realize that this positive iron is going to go with the negative hydroxide. So we know that the iron's a 3+, hydroxide's a 1-, so that means I need 3 hydroxides to go with 1 iron. So my product over here, one of them will be iron 3 hydroxide, and we'll have to decide whether it's aqueous or not in just a minute. And then the other product will be potassium with the nitrate. Now remember, potassium's a 1+, nitrate's a 1-, so that's going to be a 1-to-1 ratio, potassium nitrate. now that I've written the correct formulas, and I know they're correct because this is a 3 plus and that's a 1 minus, that means I need 3 of these to go with 1 of these, and that's a 1 plus and a 1 minus. We don't carry through subscripts. You just write the correct formula. The next thing we need to do is balance it. So when I go through and balance it, I look at iron's 1 and 1, potassium's 1 and 1, but I have 3 nitrates here, and I only have 1 nitrate here. So I need to put a 3 in front. When I did that, I have 3 potassiums, so I go back to the other side. I need to put a 3, that's 3 potassiums, 3 hydroxides, and then this side has 3 hydroxides. So after I've written the correct formula and I've balanced them, now I need to decide which one of these is aqueous and which one is solid. So remember, here, anything with group 1 is always solid, soluble, or aqueous. So we have potassium, which is group 1. Not only that, though, we also have a nitrate, which is always soluble. So we know that this one is aqueous. So that means the other one is probably solid, but you should check. So in this, we have iron hydroxide. So I look at my hydroxides down here, and it says all hydroxides would be insoluble or solids unless it's with group 1, ammonium, calcium, strontium, or barium. Well, this is iron. It doesn't include any of these, so it's got to be insoluble. So this is the solid. So that's the precipitate that forms in this reaction, right there. Now the next thing is, to practice, we're going to do the total ionic equation. And the total ionic, we're just going to dissociate everything that is aqueous. And in this case, we have 1 iron, so that's going to be an Fe 3 plus, now there's 3 nitrates, right? This subscript means there's 3 of these. So there's 3 moles of NO3, 1 minus, plus. Now this is aqueous, so it's 3 potassium, so that's 3 K plus, and then we also have, that's a 1 plus, sorry, and then we also have 3 hydroxides, so that's 3 OH, 1 minuses. Now all these ions are aqueous. I'm just not writing aqueous because I don't have enough space, but we know that ions only exist in aqueous form. Now we have the solid, so we have to leave it written as is, because it does not dissociate, and you must make sure you write the solid symbol. And then these are aqueous, so we dissociate. We have 3 potassium 1 pluses plus 3 NO3 1 minuses. So now again, I'm going to look and check to see what's the same on both sides. So this nitrate and this nitrate are exactly the same. And this potassium and this potassium are exactly the same. So those are my spectators. So my net ionic, the real reaction, what's really changing is my iron 3 plus, which is an aqueous ion, plus 3 moles of OH 1 minus, which are aqueous ions. So these are aqueous and they're charged. The change is that they now form a neutral compound that is solid. So there's the change that occurs. So this is my net ionic. And remember, I didn't have to do all of this. All I had to really do is say, okay, take the solid, write it as the product, and then on the reactant side, write the ions that make that solid. And then, of course, my spectator ions are going to be the 3 moles of potassium 1 plus and the 3 moles of nitrate, not ammonia, nitrate 1 minuses. And of course, I didn't have to write all this out. I could realize that these are a result of the product that's aqueous. and if it's aqueous, then I just dissociate it. So the spectator ions come from the product that's aqueous, and the net ionic equation comes from the solid or precipitate and the ions as the reactants that make that solid. And we will end this video on that note. Thank you.